is your TV on? If it is, that's great. You're using electricity. But if you're watching the show and your TV's not on... Anyway, what is electricity? I mean, where does it come from? Is it just sitting in the wall waiting for us to use it? Or is it constantly spilling out of sockets and we don't notice it? And how can something so powerful be invisible? Well, electricity is the flow of tiny particles called electrons. And they're not just smaller than atoms, they're actually part of atoms. Take a look at this. It's our battery-powered electrical circuit of science. We're going to run this big light with this big battery. Watch.
Attention, ILM.
See, right now, electrons can flow from this side of the battery, through this wire, through the switch, through this wire, into the light, and back to this side of the battery. They're flowing in a closed path, what scientists call an electrical circuit. Now, circuit, that's from an old word for go around. So electrons, right now, can go around an electrical circuit. The flow of electrons is a lot like the flow of water. No kidding. Watch. When I operate this great big water pump of science, water goes through this hose into this box and makes this water wheel go around. And it goes out the other side through this hose back to the pump. It's a closed path for the flow of water. It's a water circuit. It's just like the flow of electrons through an electrical circuit. Electricity is a very versatile form of energy. The same electrons that are making the light light up are making a motor go around. See, electricity can do all kinds of different jobs, and they're all done with electrons.
Electrons flowing through a wire are a lot like water flowing through a hose. When we got the flow going, we can do work.
Bumper cars have electric motors. The electricity runs from the rod that touches the ceiling, through the electric motor in the car, and then to the floor. So you don't get a shock from the floor unless you can touch the ceiling at the same time. Otherwise, it's not a complete circuit. Science!
Science is cool! Check this out. It's an electric train. It has two rails. Electricity goes in one side, through the motor and the engine, then back out the other side. It's a circuit.
Electricity is the flow of electrons. Electrons are the tiny particles that buzz around the outside of atoms. Now, when electrons are able to jump from one atom to another, well, that's the flow of electricity. Now, in some materials, like metals, electrons can jump from atom to atom very easily. Atoms and metals are like a bunch of beehives. The electrons are like the bees buzzing around the hives. When electricity flows, it's like the bees jumping from hive to hive. That's electricity.
You can make an electrical circuit and figure out what things let electrons go through them and what things don't. Hook up a circuit like this. The tricky part of a circuit like this is getting the batteries to stay put. We've got it all worked out. Test things and see if electricity goes through them and what things don't. It seems that metal things carry electricity pretty well, and rubber and plastic things don't. Try this, a pencil. Now a pencil slit in half. Check it out. It changes. The circuit's complete. But the pencil lead is holding some electricity back. Things that let electricity go through them are called conductors. Things that don't are called insulators. This can be called a resistor. It's somewhere in between a conductor and an insulator. It lets some electrons go through, but not all. Wild!
Electrical circuits and water circuits both have pressure and flow. Think about it. Sometimes when you go up to a drinking fountain, the water comes out just fine. But other times, at other drinking fountains, it hardly comes out at all. That's because it doesn't have enough pressure. In electrical circuits, there's pressure too. It's called voltage. The higher the voltage, the more electrons want to jump. Now, the number of electrons that's flowing through a wire we call amperage, or just amps. Now, amps are like the amount of water that's coming out of a drinking fountain. The more amps, the more electrons. So in electricity, we end up with two things: voltage, or volts, and amperage, or amps. Volts and amps. Volts and amps. Volts and amps. The same way with water, we end up with pressure and flow. Pressure and flow. Pressure and flow. Now, the combination of volts and amps we call watts.
What?
Watts. Now, you know about watts. A 100-watt bulb needs more watts than a 40-watt bulb. I mean, it's a bigger number, more watts.
What?
So watts. Boy, that's a lot of watts. Okay, we're gonna do some power exercising. Ready? See, the generator is connected to the exercise bicycle wheel. We're running the generator, that's completing a circuit, and we're turning that light bulb on. It takes a lot of power to run an electric light bulb. It takes a lot of watts.
What?
Watts! Electrical power. You see, a 100-watt light bulb takes 100 watts of power. That's a lot of power. That's a lot of watts. Make it burn.
Okay, it's burned. Can we stop now?
Next.
Batteries and hot dogs are a lot alike.
Oh.
No kidding. A hot dog has a piece of meat with a roll around it. Well, inside a battery, there's a long rod with a can around it. Now, between the rod and the can is some goopy chemicals called electrolytes. Now, that's what makes electricity flow. Between a hot dog and the roll are some goopy chemicals called mustard and relish. So instead of poles, it has rolls. Now, if you put a hot dog in a flashlight, nothing happens. Duh. That's because a hot dog doesn't have the right chemicals to make electricity flow. But a battery does. And those chemicals are what make electricity flow from one end of the battery to the other. Now, when the chemicals are used up, the electricity stops and the battery's dead. But batteries are a good, compact source of energy. So are hot dogs. Electricity can be dangerous. There's enough power in a wall socket like this to burn your skin. Just be careful. Hey, imagine if you had all this water falling from here down to there. over 100 meters. You could generate 6.5 million kilowatts of electricity. That's a lot of watts.
What?
It's Grand Coulee Dam in Washington State in the USA. If you've ever lifted a bucket of water, you know, it's pretty heavy. Well, imagine how heavy the water is behind that dam. It's over 100 meters high. It's almost 2 kilometers long. That's a lot of water. So as the water flows from the top to the bottom, it runs huge generators. No, really huge. I mean, big. I mean, very big. I mean, bigly, hugely big generators. 6,949,000 kilowatts. That's a lot of watts.
What?
Watts. Electric power. Electric power that runs from here to millions of homes so that people like you can watch television and play video games and pop popcorn in your microwave ovens and have toasted tarts on your toaster in the morning at breakfast. Man, that thing is big. We use electricity all day. Most of the time, we don't even think about where it comes from. Once it's generated, electricity may travel hundreds of kilometers through power lines before it gets to our homes. Whoa. When we make electricity with a magnet and a coil of wire, either the magnet or the coil has to be moving. Now notice that the coil is either right side up or upside down. Right side up, upside down. And the electricity that gets made goes this way or that way. This way, that way. We say it's alternating. We call it alternating current, or AC. Now, when we make electricity with batteries, the electricity only goes in one direction. We say it's direct current, or DC. So this is DC, AC, and PC. PC, that's what I call popcorn. Birds can safely sit on one of the wires on power lines because then their bodies don't complete a circuit. The monsters in science fiction movies, they complete circuits. Ouch.
For electricity to do work, it has to flow in a complete loop. That's called a circuit. Turning on a switch completes a circuit. Turning it off breaks the loop.
Hey, turn on the lights. I can't see. Ooh.
So you probably know that everything around you is made up of tiny particles called atoms. The simplified model of an atom has a positively charged center called the nucleus, and you have negatively charged electrons orbiting around it. The terms positively charged and negatively charged are arbitrary, and the important thing to know is that things with opposite charges attract each other, and things with the same charge repel each other. So the positive nucleus of the atom will attract negative electrons, but if electrons get too close to each other, they'll push each other away. In most solid materials, the atoms and their electrons just sit there and don't really move around. But in metals like copper, the electrons have the ability to move around. The positive nuclei stay in the same place, preserving the structure of the metal, but the electrons can drift around from atom to atom. But since the negatively charged electrons repel each other, when you move one electron from atom to atom, you'll also move other electrons from atom to atom. For example, let's say you have a wire that's only one atom thick. And just so you know, I'm massively oversimplifying things here by showing you only one electron per atom. Then let's say that you force the first electron in line to jump to the second atom in line. The electrons will all push each other around at the same time, kind of like a conga line. Even though each electron is only jumping a tiny distance, this overall flow happens close to the speed of light. And that's basically what the flow of electricity is. When electrons are flowing through something, you can say that electric current is flowing. Now, how do we measure electric current? Well, you've probably heard of the term amp, which is short for ampere. An ampere refers to the amount of electrons that are flowing per second through something that conducts electricity. 1 ampere is equivalent to 6.24 times 10 to the power of 18 electrons flowing per second. You don't really need to memorize that number, but you should understand that electrical current refers to the amount of electron flow, and that 1 amp means that a lot of electrons are flowing. And obviously 2 amps means that twice the electrons are flowing. And if you want, you can use the analogy of the amount of water flowing through a pipe. Okay, just so you have a frame of reference, here are a few examples of different currents you might encounter in your day-to-day life. Alright, now's the perfect time to talk about electric circuits. An electric circuit is a closed loop where current can flow around. In this example of a flashlight, electrons can flow from the battery through the copper wire, through the light, and through another piece of wire to the other side of the battery. Now remember, when current is flowing here, all the electrons are moving at the same time. Over here, the negative terminal of the battery is pushing the negative electrons away, and those electrons are pushing other electrons away. And this keeps happening throughout the circuit, allowing energy to be transferred from the battery to the light. But if you were to cut one of the wires here, you would no longer have a complete circuit. The electrons can't just jump through the air from one wire to another. So if electrons can't push each other around in a complete loop, no current can flow. When there's no current flowing, there can't be any transfer of energy, so the light stays off. And this is how electric switches work. The switch has 2 pieces of metal inside it, and when the pieces of metal touch, you get a complete circuit and the light turns on. When the pieces of metal are pulled apart, it becomes an open circuit and the light turns off. And this is also how fuses work. Right now I have 5 amps flowing through this fuse, which is rated for 15 amps. But when I suddenly draw 30 amps, the fuse melts, opens the circuit, and prevents any current from flowing until the fuse is replaced. Very handy for when you don't want to die in a terrible fire. Now there's one more tricky thing about electric current that most people don't know. There are actually 2 naming systems for electric current. One is called conventional current and the other is called electron flow. Heard that current flows from positive to negative. So you might imagine that with this circuit, current is flowing from the positive side of the battery towards the negative side of the battery. This system of current flowing from positive all electrical engineers use, and it's called conventional current. However, conventional current is wrong. Back in the early days when scientists were still figuring out the basics of electricity, they didn't know whether it was the protons or the electrons that were flowing. They made a guess and thought that current flowed from positive to negative, but the reality is that the actual flow of electrons goes from negative to positive. Unfortunately, every single formula that we use in electronics is based around the mistake of assuming that current flows from positive to negative. The good news is that the formulas are consistent, and whenever we do any math in electrical engineering, we use this system of conventional current, and it works. So you can just pretend that electrons are moving from positive to negative, even though that's backwards to reality.
Thank you.